Okay, we're live. Well, actually, it's not live. This is recorded. We're recording. I'm skipping over the last couple of examples in the slide deck, and we'll come back to those. What I want to do first is just go through Kirchhoff's laws, which we've already been introduced to, and show you an example of this, and then we'll work through some problems that. Some of the example problems that are in the slide deck. Okay, Monday we're going to cover RC circuits. Okay, and then Wednesday and Thursday will just be review for Friday's test. All right. Okay, so Kirchhoff's laws, we've already looked at both of these. The loop law just says that as you go around any loop, that the sum of the voltages is 0, so that means that I go up V1, I'm going to go down across this one and down across this one, get back to whatever I started with. These typically, you set one of these nodes to be ground, so you'll see this in some figures where this just means ground. That means the voltage is 0 for wherever that is. So then you can say that's 0, and then I've got a voltage here and so on. Now your textbook talks about it doesn't matter which loop you choose to go around. But when you have a circuit with multiple loops, you can only choose, at some point you start getting redundant information, okay? So just as an example, in this case we have 2 loops, and we can choose to apply Kirchhoff's loop law to the left loop and then the right loop. We could choose to apply Kirchhoff's law to the left loop and the big outer loop, or we could do the right loop and the big outer loop. If you do all 3, left, right, and big outer loop, then you're getting redundant information. There's no new information that is presented mathematically in the equations that we're going to develop. Okay? So here's my recommendation is you just stick to the small loops, okay? So for example, I would do this little loop and that little loop. Don't go around outside, okay? This is actually it's a much more systematic and robust analysis if you just go around the interior loops, however many those are, okay? And so just remember that the loop law says that the sum of the voltages is equal to 0 as you go around that loop. Does that show up okay? It doesn't look like it shows up very well, does it? Let's try this. Does that show up better?
Yeah. Oh, yeah.
Okay. Sum of the voltages equals 0. Okay. Now, the junction law says that whatever currents are coming into and out of a junction have to add up to 0. So essentially, the junction law is the sum of the currents is equal to 0, all right, where incoming currents would be positive and outgoing currents would be negative. The other way that you could state the junction law is that the sum of the incoming currents has to equal the sum of the outgoing currents, okay? So just as an example here, we've got junction B, and if we look, I've got I1 coming in. This is I1. I2 going out, that's I2 right there, and I3 also going out. Okay? So if I take those, I can express the junction law in one of 2 ways. I can say that the incoming current, I1, is equal to the sum of all of the outgoing currents, I2 plus I3. The other way, sorry, let me pull that down. The other way that I could state this is that I can have the incoming currents be positive currents, I1, and then the outgoing currents be negative currents, I2 minus I3 equals 0. Hopefully you can see that these are mathematically equivalent. I have I1 equals I2 plus I3, or I1 minus I2 minus I3 equals 0. All right? So these are the 2 laws, okay? And we're going to practice applying these to some different circuits, and the goal is to identify all the currents and all the voltages that are present in a circuit, okay? So the approach is we're going to use Kirchhoff's loop law to sum the voltages around all the loops, and then we're going to use Kirchhoff's current law to sum the currents at the junctions. Typically, you're only going to need to look at one junction in the circuits that we're going to look at, okay? And then we have a system, we build up a system of equations, and then we have to solve that system of equations, all right? So that's the goal. So let me just show you, I think the best way to do this is by looking at an example. Okay, does that show up okay? All right, so in this example, we've got two loops, okay? And this is going to be the case essentially for everything that you're going to do. You're going to have two loops. If you introduce a third loop, you would have, the way that we're going to solve these, you would have a system of 6 equations and 6 unknowns. It's doable, right? But it sounds kind of tedious, all right? So we're not going to extend that far. There are more elegant analyses that we can do, but that's really the subject of like a circuits class. If you're going to take circuits in the fall, we're going to do mesh and nodal analyses, which are very systematic and a little more elegant than what we get to learn in physics, okay? All right, so the first thing that we want to do is apply Kirchhoff's loop law. Now, in your textbook, this example, they do the outer loop and then the bottom loop. We're just going to stick with my recommendation, which is you're going to do both little loops, okay? This is a 2-loop circuit, all right? And so we're going to start here, all right? And we're going to apply Kirchhoff's loop law, all right? So they have the currents listed, okay? We have I2 listed here. If they don't have them, you need to label them. I1 and I3. These are all labeled on the circuit, okay? The directions matter. You have to, whenever you assign currents, you assign I1 with a direction, I2 with a direction, I3 with a direction. The directions matter because as you go across elements, the current or the voltage is either going to go up or down based on what's the direction of the current, okay? So we're going to start here at this blue dot, and we're going to go around the top loop in a clockwise direction. It doesn't matter which way you go. You can go counterclockwise, you can go clockwise, you just have to stay consistent. Okay, so we're going to go in this direction. All right, the first element that we get to is a resistor. Okay, this is a 1 ohm resistor. So what is the voltage in this direction? Does the voltage go up or down if I'm going in this direction?
Down.
It goes down. Why does the voltage go down? V equals IR, and I'm going in the direction of the labeled current. Does that make sense? The current, in the direction of the current, the voltage is going to drop. Okay? So I'm going to have in my in the top loop, so we'll say this is the top loop. I'm going to have this. I'm going to go down I1 times 1 ohm, right? Because this is V equals IR. So that's the first term. And I'm going down, so I'm going to have a negative sign here. Okay? And then I get here. What happens as I go across this next element?
Added charge.
I'm not adding charge. What am I adding? Voltage. I'm adding voltage, right? Those are different words. They mean different things. So I'm going to add voltage. So I'm adding 0.5 volts. Okay? And then I'm going to hit this next one. And what happens at this point? This is a 2 ohm resistor.
Voltage goes down.
Voltage goes down, and it's going to go down according to IR. What is the current going through this resistor? I1. That's right. And so we'll say this is minus 2 I1. I'm going to drop all the units, so hopefully I don't run out of space over here.
And the current's the same because they're all in series?
Yes. Yes. All right, and then I'm going to keep going. Where's the next element in this loop? There's no elements here.
The jump.
Nope, there's an element right here.
Oh, because we're looking at the.
Yeah, we're doing the top loop, right? We got to get all the way back to where we started. We started at this little F right here. We got to get all the way back. Okay, so I'm going to get back here, and now I've got R3, this 1 ohm resistor. Okay, so is the voltage going to increase or decrease across this resistor?
Decrease.
It's going to decrease. Why is it going to decrease?
Because the resistivity goes up, the V equals II.
Well, because I3 is pointing to the left in the direction that I'm going, right? Okay, so I'm going to go down 1 I3 because I3 is what's going through R3. It's not I1 anymore, it's I3.
Oh. So
You see that?
At what point does it switch to I3?
When you're in this
Okay.
this leg right here, because I3 is the current that's going into this junction right here from this direction.
So after the junction is when the label of the current changes.
Yeah, anytime you move into a different segment of wire, you're going to have a different current that hopefully you have labeled. Okay? All right, so this is going to go down 1 I3 minus I3. And then what happens here?
Complete the loop. Oh, well, it gets more charge.
Plus
More voltage.
0.6. Okay, and then we dropped all of our units because I wasn't going to run out of space. Okay, and for all of these, as long as your units are volts, ohms, amps, etc., then we can just use the numbers in our equations. You just have to be careful because if you have a kilo ohm resistor, that's 1,000 ohms. So you have to include that information. Okay, so that's the top loop. Let's do the bottom loop. And we'll do the same thing. We're going to start at F, and then we'll go around in a clockwise manner, just like we did before. We'll get back to F, okay? So let's go. Here we go. What do we get to first?
Oh, it's going that way?
Yeah, we're gonna go clockwise around the bottom loop.
Because voltage, but it's going from the positive to the negative.
So I'm going down.
So this is.
So I'm going to go down 0.6 volts, okay? All right, so that's right here. All right, and then what happens when I get to this resistor? Do I go up or down in voltage?
Why are you going that way?
Because I'm going clockwise, because I chose clockwise. Why not?
It'll equal 0 either way. 'Cause of the-
So you could you have done it counterclockwise?
Yes,
on
you
this?
could have, but I want to show you that
Cool.
you can go clockwise too. And I want you to know what happens when I get to this resistor. Is the voltage going up or down? Up. It's going up because I'm going against the current. Yes.
So if we pick clockwise for loop 1, do we have to go clockwise for loop 2?
No.
No.
No. You can do whatever you want.
But this is our-
I think it's a lot easier to just be systematic and say, I'm always going to do clockwise. But you can choose either way, right? Because mathematically, going clockwise versus counterclockwise is multiplying the whole equation by -1 or 1, right? Depending on which way you go, right? So that's all that's happening. Okay, so I'm going to go up I3. All right, because it's 1 times I3. All right, I'm going to go up. Notice that I3 is pointing in this direction. Think about each of these resistors as a waterfall. Right? If I'm swimming upstream and I get to this waterfall, I'm going to have to climb the waterfall, right? I'm going to have to go up because the current is going against the direction that I'm traveling. Okay? All right, let's keep going. We get to R6. This is 2 ohm resistor. Okay, which way is the current going through this resistor? What current is going through that resistor? I2. And which way is it going? It's going this way and this way, right? Okay, so am I going up or down? I'm going up. So I'm going to go up 2I2. Okay, does that make sense? I'm going to keep going. I get to this resistor. Now what am I doing? Am I going up or down? Still going up because I2, I'm swimming upstream. On this whole loop, I'm swimming upstream because I chose to go clockwise. So then I'm going to go 1 I2, so that's plus I2. All right, and then let's keep going. What happens when I get here to this resistor? Or, sorry, this voltage source?
Minus 2.3.
Minus 2.3. Okay, and then what happens when I get to this resistor right here?
Once again.
I go up
Plus
5I2. All right, so I have now done Kirchhoff's loop law for both loops, okay? Now, how many things do we not know in these equations? I don't know I1, I3, I2. So the problem is I have 3 equations and 3 unknowns. So I need 3 equations and 2 unknowns. I need one more equation. Where do we get that from? We get that from the junction law. So now I can look over here at the junction law and I can say that I3 is coming into this junction. I1 and I2 are leaving that junction. Yeah, so I could say that like I3 equals I1 plus I2, right? So there's different ways that we can express the junction law. You can do negative I1 minus I2 plus I3, right? You just have to be consistent when you apply the junction law. Now I have 3 equations and 3 unknowns, and I need to solve this, okay? So how do we solve 3 equations and 3 unknowns? Well, we do that with our calculator, okay? So in order to solve this with our calculator, we have to recognize something very important about this system of equations. This is a linear system of equations, okay? So that means that I've got I1, I2, and I3, and I don't have I1 squared. I don't have the sine of I1. I don't have exponential, right? It's a linear system of equations. It's not quadratic. It's not, it's not polynomial anything. It's not trigonometric, right? It is a linear system of equations. This will be true for all of the resistor voltage, sources that we're going to deal with. They're all going to obey this kind of rule. So what we need to do is organize these 3 equations into a real systematic, expression, okay? And this is what I want to do. I want to take the first equation, all of these equations, I'm going to organize into something times I1 plus something else times I2 plus something else times I3 equals whatever's left over, okay? And I need them to be in that order, okay? So let's do the first one. Let's look at this top one here. I need something times I1. Well, let's look. I've got a negative 1 I1 here, and I have a negative 2 I1 here. So I've got negative 3 I1, okay? So I can just write that out. Negative 3 I1, okay? So that's all my I1 terms there, all right? Now I want to do something times I2. Well, how many I2s are present in the equation? None. So what am I going to write? I'm going to write plus 0 I2. Include I2 even if it's not there. All right? And then I want to do I3. Well, what do I see here? For I3, I have negative 1 I3. So that's negative I3. And then this is going to equal, I got to move everything else to the other side of the equation. Okay, so that's the 0.5 and the 0.6. So I'm going to move those to the other side of the equation, and I'm going to get negative 1.1. Does everybody see what we did? Does that make sense, what we did? We're organizing the equation into I1 terms, I2 terms, and I3 terms, and then we're putting all the other stuff on the other side of the equation. Okay? Hopefully you can see we can multiply this through by -1 to make everything positive, if you want to. If you're a positive kind of person, let's go through and multiply all these by -1, noting that if I multiply positive 0 by -1, that's still positive 0, because adding or subtracting 0 is the same thing. Okay? All right, so let's look at the next one, the bottom one here. Okay, the bottom loop, I've got this equation right here. So how many I1s do I have? 0. So I'm going to do 0 I1. All right. Okay, and then how many I2s do I have? I got 2, 3, and 5. That's 8. Plus 8 I2. All right. And then how many I3s do I have? 1 I3. Okay, and then what's left over? I need to move the 0.6, the negative 0.6, and the 2.3 to the other side. So what am I going to get on the other side of the equation? 2.9. Okay, and lastly, I need to do this equation right here. I need to get it in the same exact form. Okay, so I can move like I3 over here, or I can move I1 and I2 to the other side, but we'll just do I1 and we'll move I3 over. So that way we get I1 plus I2 minus I3 equals 0. Okay. Okay, so notice that we have everything, each one of these equations is now in this exact same form. I have something times I1 plus something else times I2 plus, I3 equals whatever the constants are. Okay. All right. So we're going to do that for all three equations, and then we're going to plug it into our calculator. All right. So the way that we're going to plug this into our calculator, we need these coefficients that are in front of all of those terms, and we need what's over here. Okay, so those are the things that we need. All right, so let me pull in my calculator. Here we go. Okay, so in order to solve this, this is a system of linear equations, and there's something called system solve on your calculator. It's right here. It's this button. Oh, it's kind of fuzzy, sorry. But it is second system solve. You guys, I think y'all have done the 2x2s. Have y'all done 2x2s with this? Maybe? Anybody? No? Okay. This is a 3x3 system of linear equations. So I'm going to select 3x3 because I have 3 equations and 3 unknowns. If you have 4 equations and 4 unknowns, sorry, the TI-36X Pro isn't for you. All right, so we're going to hit enter. All right, and now what we have to do is enter in, see, each one of these needs to go into its respective place. So this top one, I need to enter in a 3. Then I need to enter in 0. Then I need to enter in 1. And then I need to enter in 1.1. So the top row should look just like that, 3, 0, 1, 1.1. The i's are gone. They're still there, but the calculator knows that they're there. Okay? Okay, does everybody see that? That make sense? Yes.
We need to make that a positive, or do we plug it in negative?
You can plug them all in negative. Yeah. All right, and then for the second row, I'm going to have 0, 8, 1, and 2.9. All right, so I did that one. And then the last one, I have a 1, a 1, and a negative 1, and a 0. Okay? And it should look like that. All right? Comprende? That make sense? Okay, you see the pattern? And then you hit enter to solve it. Now, this doesn't know that we're using the letters I1, I2, and I3. All right? The calculator thinks these are X, Y's, and Z's. So it is going to give us the first, it's going to give us this answer first, then this one, and then this one. So when we look at the calculator, it's going to give us X equals X equals 1/5. So in the calculator, X corresponds to this first row, and this is 1/5. The units of this are amps because these are currents. And then we hit enter. Y is going to equal the next thing. In this case, that's I2, and that's 3/10 of an amp. And then lastly, Z, which is going to equal I3, and that is 1/2 of an amp. Okay. All right, does everybody see how to do that? Okay, so your job is to analyze the circuit, set up the system of equations, and then please use your calculator. Now these aren't like super hard. You can do substitutions and you can hack through all the algebra. I'm fine if you want to do that. When I'm grading these on the test, I won't pay any attention to your algebra. I'll just look at, did you set up your equations right, and did you get the right answer, right? So this is sufficient for the analysis of this circuit. Okay. All right. Okay. Any questions? Y'all ready to? You guys ready to try some? Okay. So we have a couple left over from last lecture, but I thought maybe we should just try Kirchhoff's law one first.
Can you just write what your equation would be real quick on that one?
What do you mean what my equation would be?
What the bottom equation would have been if you did it counterclockwise?
Oh, if you did it counterclockwise?
Yes. Is it just your...
It would be positive 0.6 minus I3 minus plus minus.
All right.
You'd just be multiplying everything by -1.
Okay. And then do you need to do any different step later on if you do that? Or you
No.
Okay.
Nope. It's all fine. Yeah.
All right.
Did that give you some heartburn, like going the wrong way?
Terribly. Yeah.
Now, okay, let me also just mention a couple of other things about this, right? In this case, they told us this is I1, that's I2, and that's I3, okay? When you're initially analyzing a circuit, you may not know the direction of the current. So what do?
It depends on the direction of where the volts are being applied. Because the volts are being applied in a specific direction where it's plus or minus. Is it not following that direction?
Maybe, maybe not. It depends on the rest of the circuit, right? So the whole circuit acts together. And so one component affects another one. And so if you may not know which direction the current should go. In that case, you just guess. Pick a direction. What happens if you're wrong?
Just negative?
You'll have a negative answer here. Like if you mislabeled this and you're like, okay, I3 is going to go in this direction, and you think I3 is going to go to the right. Well, when you solve this, this I3, that would be a positive term, that would be a negative, like all the signs would be wrong or different, okay? And then when you get here, I3 would equal -1/2. So it's fine if you've got, if you have the wrong direction for a current, or all the currents. It doesn't matter. You can have them all wrong. They'll just all be negative, meaning they're going in the opposite direction that you labeled them. Okay, the math will take care of, anything that you do with like guessing the wrong direction for a current. Yes.
I know you said to do interior loops, but could you have done like the loops that I guess were on the diagram? Like, could you pick different loops to do?
Yeah, you can. Yeah.
Okay. Well, then what stops you from like why couldn't you do like 3 loops where you do like the top, the bottom, and then all of them together?
So if you do that, you don't introduce any new information with Kirchhoff's loop law.
Okay.
You could get the same information algebraically by, say, adding these two equations together, or taking their difference. So you can get to the outer loop from these two loops. The new information that you have to have is the junction law. Yeah. Yes, Abigail.
Can you explain how you did the junction law one more time? How you chose I3 to be equal to I12?
Yeah, so the junction law, we just look at one of the junctions, okay, and we look at this one right here, and we see that there's I1 coming out, I2 coming out, and I3 coming in. So I just said that the incoming current, I3, has to equal the sum of the outgoing currents, I1 plus I2. And that is essentially the junction law. The other way that we could have algebraically written it is, I've got a positive I3 minus I1 minus I2 equals 0. So you can also do it that way. Algebraically, it's the same thing. That's kind of what we wound up doing here, right? Okay, so let's do a...
And so would it be wrong if you did I2 equals negative I1 minus I3? Or something like that?
I2 equals negative I1
Oh, I guess that would be
plus
so,
I3. Yeah,
so
any
any way you combine. Okay.
I mean, you can rearrange this algebraic expression however you want, right? I think the two ways that's most natural to apply the junction law are incoming currents equal outgoing currents, or incoming currents minus outgoing currents equals 0. So one of those, right? You could also do outgoing currents minus incoming currents equals 0, right? That doesn't matter a whole lot. Okay, so this is a good one. You guys tried this one. This is just one loop. So you don't really need the full, capabilities of the TI-36X Pro, but you will on the next one. So just hang tight. We'll work through a couple of examples. So I want to give you guys just a second to do this one. We might have to work the other ones next week when we get back. Should I pause my video or make them suffer through?
No, make them suffer.
Make them suffer through? Okay. All right. Disable fast forwarding.
Yeah.
Can I do that on YouTube?
I don't think so.
No, you
Yeah.
can't. It's already there.
They're probably already listening to me at 1.5 speed anyways.
Or 2 times.
Or 2 times, yeah.
It's so funny to listen to the high pitched voice, sometimes though. So I understand.
If you want a better image, you can grab this straight from the slide deck on Moodle.
I think randomly change the direction, and then you get a negative value.
Pick a direction. It doesn't matter.
And then that's which direction makes sense.
No, because if you guess wrong,
No,
it'll be
if
negative.
you pick a direction.
So don't stress about it. You just pick a direction.
And you get a negative value, and that just means it's counterclockwise. Or the negative sign tells you what direction it is compared to the direction you chose. just seems wrong.
It's fine.
It's fine.
This is essentially what you do when you charge your cell phone battery with an external battery pack.
Yeah, I wonder what
The voltages are pointing in the same direction. It's like feeding the
Interesting.
Maybe I just didn't remember that.
So like what's happening in the top wire? It's just like built, I don't know, never mind.
current flowing through it.
And I guess that's what I'm gonna figure out.
Yeah, you gotta figure out what the current is.
Oh, that's
Also,
twenty-four
this is
volts.
only
Right.
one.
I just wrote down something. I could just choose
No, you gotta pick a direction for the current. You think what-
Yes, I think so.
like current, like your current is gonna go this way through that. Or sorry, that.
Well, I wrote it down, for one, I wrote it down wrong. But
But no,
the
you're gonna
the
drop.
voltage being
If you're going
subtracted,
this
if you're going clockwise.
voltage drop.
V1
That's a
is
voltage.
subtract- If you go clockwise, V1 is subtracted.
Voltage increases.
24.
Because that's like the negative positive.
Well, I went counterclockwise.
Okay.
The direction of the current
Negative
one
24.
affects what happens in the resistors.
Plus
Not what happens in the voltage.
Minus 12 plus 10.
So the voltage is,
Plus 12.
the power supplies, those
Is it?
will have like.
Those are going in opposite, those two voltages are
They're going in
opposite
opposite directions. Was this 12 instead?
So if we're going V4,
Maybe it's 22.
this would be a negative minus 10, minus 12.
Is there, that's a good question. Is there a new current? So if you have this current going in this direction, it has to go here, right? I mean, the current has to be
Lost in the sauce.
right? Is there a way for it to split away and go somewhere else? All right, let's go ahead and work through this. All right, let's see. So which way do we want the current to go? Clockwise, counterclockwise, clockwise? Clockwise. Okay, clockwise is in this direction. Okay. And if we choose that direction for current, then it's the same current going all the way around the loop. Okay? Right? And so then what we want to do is just apply Kirchhoff's loop law. So we can start, say, down here at C, and then you guys want to go clockwise or counterclockwise around the loop? Clockwise? Yeah, it's easier to go in the direction of the current. So then we're going to go this way. Okay, we hit this voltage source, so that we're going, what, up 24 volts? So we got 24. Okay. And then what happens when we get to this resistor? We go down, because we're going in the direction of the current. We're going down 20I, right? Because this is a resistor, follows Ohm's law. And then we're going to go down 10I. Okay, and then we're going to go down 12 volts because we're going down this voltage source. And then we're going to go finally down 30I. And this equals 0. Now this one, hopefully, you didn't need the equation solver. We can just solve this by adding up, moving all the i's over, and so you get I equals 12 over, let's see, 20, 30, 60. Which is, what is that, 2/6? 1/3? Is that 1/3? 1/5? Oh, 1/5.
Oh, yeah, you go up that way. How did I do that?
And because it's positive, that means we guessed the right direction for current.
Because so you won't have a negative current then? That can't be an answer?
You won't have a negative current. You could have, if you guessed the other direction for current, it would be negative.
Will the correct answer ever be negative?
What do you mean?
Like the correct answer will never have negative amps.
If you have negative amps, that means that the labeled direction for the current
Is wrong.
is backwards from what's really happening. That's all that means.
Why were the resistor values negative?
The resistor values are not negative.
Or why is
There's just a
the
dab.
20? Why is the resistor multiplied by the current negative?
Because what we're doing is delta V for this resistor goes down.
And
So you're going down IR3, which is 20I. So you're going down 20I. So we're applying Ohm's law to each resistor.
how do you know which way?
Oh, sorry, I did that wrong. We're going this way. Sorry.
How do
Here,
you
we're
know,
going down voltage. There you
how do
go.
you know which way goes down the resistor?
So you're going down in voltage if you're going in the direction of the current.
Oh, okay. Okay.
Like if you're going in the direction of the current over a waterfall, you're going down.
Okay.
If you're going against the current, you're going up.
All right.
So just remember, current, even though we're talking about, conventional current, it's kind of just think about I'm walking along a river in the mountains,
Okay.
and I'm walking against the current. Am I going uphill or downhill? I'm going uphill, right? I'm walking with the current. I'm going downhill. When you get to the voltage sources, you just have to look at those. And you have to say, okay, am I going up or down based on which direction you're going across them? The direction of the current through the power supply doesn't really affect what's happening to the voltage across that power supply. So if you're curious, what's happening in this circuit is this battery is sending current into this battery. And so this would be kind of like a rechargeable battery, right? It would be absorbing power from this one as it gains, energy.
Is that because the left battery has more voltage that it's starting? Or I guess.
Yeah, that's right. Yeah.
Okay.
Yeah, if you were to make this a smaller voltage, it would be going in the other direction. Now, hopefully it's a rechargeable battery. Not all batteries are rechargeable. If it's not, you can have bad stuff can happen. Anyways, okay, we're going to stop there. We have lots more practice that we can do next week.